Hello guys, today we will talk about minimal spanning tree. And firstly, we remember what is spanning tree. And if we have undirected graph, for example, without weights, we can, and we, for example, have one connected component, then we say that tree as a subgraph is a spanning tree when it includes all the vertices in the graph. And of course, if we have more than one component, we say that it isn't there isn't a spanning tree, and for example, we can say that there is a spanning forest. Okay. So today we'll work with some algorithms about minimum spanning tree, and as you know, we can say that each edges have weights, yeah, and then we say that if we have some subgraphs, for example, some spanning tree, we can sum all the weights of the edges in this subgraph. Okay. For example, in this subgraph that I emphasize by orange color, I can say that sum of the weights equal to 1 plus 2 plus 2 plus 2 plus 1 plus 2 plus 3. Yeah, and it's equal to 11. Yeah. So we say that spanning tree is a minimum spanning tree, and we write MST shortly. Yeah? If the sum of the weights is the minimal in the set of the minimals in the set of all spanning trees. Okay. So if we have very dense graph, we of course have a lot of spanning trees, and we say that minimum spanning tree it is one or several spanning trees that have the minimal weights as a sum of weights of edges in this tree. Okay, understandable? Nice. Oh, why? Yeah. So, firstly, we'll talk about some properties about minimal spanning trees, and firstly about minimum cost edge. For example, we can see in the previous slide, we can see that in this graph we have two edges with the minimal weight. This is the first and this is the second. Yeah, and then we say that if we have if, for example, edge E has minimum weight, so there is some minimal spanning trees that contain this edge. There exists, of course. So, firstly, why? Oh, yeah. No, first theorem was about existence of a minimal spanning tree. Yeah, why minimal spanning tree exists in each connected graph? We say that if we have connected graph, we can have a set of the trees, but that set always finite is finite. Yeah. So if we have finite subgraphs, we can sum in each graph some weights of the edges, and then say that we have finite numbers and find the minimum of them. Yeah. Do we need to set example of this for search why we can find minimum spanning tree, or it is simple? Is it simple for you? Why each weighted connected component or weighted connected graph has a minimum spanning tree? Is it simple? No? Yes? Yes. Okay. Uh, and can I see the chat in the Zoom? But now I don't see it. Oh, thank you. Okay. Then, then second theorem about edge with minimum weight. Yeah. And we will say that, for example, if there is only one edge with minimum weight, every remaining spanning tree contain it. Why it is true? Of course, you can see and you can read the proof of this theorem, but we can draw some example to imagine why this proof is true. Okay, so let's imagine that we have graph for example with weights. I draw it with the color. 1, 2, 3, 2. Oh, let's set it's 4. Okay, and we see that in this graph we have only one edge with the cost 1, that is the minimum of the weights of the edges. Yeah. And then we say that if we find a minimal spanning tree, yeah, without this edge, for example, I can emphasize it with green color. For example, if it is a minimal spanning tree, yeah, then we say that when we add edge with the minimal cost, for example, this edge I can name as edge E, yeah, that connect O and V. And I name it like T. If we oh, sorry, yeah, I understand you. Yeah. It was me. It was my fault. Can you see this green color on the slides? Yeah. Okay. Then we can set subgraph g with the prime equal to t plus he. Yeah, and say that in this subgraph we have only one circle. Yeah? This. And in this circle we have not only E but edges, for example, U, edge connected U with, for example, vertex T. And as E has a minimum of weights of edges, we say that edge is it visible in the nice edge UT is bigger weight than weight of the E. Yeah. So we say that if, for example, we remove H U T, then we get G with 2 primes equal to G with prime minus H U T. Then we get new minimal spanning tree. And for example, if we can find sums of weights of T and G prime, we can see that the difference between them equal to difference between weight of E and weight of this edge. Yeah, because all the others edges are in all minimal spanning trees, so they're includes in both of these sums and disappear when we find a difference of them. Okay, and then it is equal to difference between weight of E and weight of H UT. And because of minimum of weight of E, we can say that it is smaller than 0. Then we say that as the consequence, we say that weight of G with 2 primes, weight of this graph is minor than weight of T. And so we have contradiction because firstly we say that T is a minimal spanning tree. Yeah, understandable. And in this proof, I shortly write this explanation.
But what is the minimum spanning tree in this graph?
In this graph, I think not T or G with 2 primes. It was only example that if we have tree without minimal edge, we can find a tree with minor weight of it. And of course, in this graph, if it is understandable to yeah, from T to I try to find, for example, red. Okay, and if we add these edges. Yeah, I think it is a minimal spanning tree, or that is the real minimal spanning tree of this graph. And it is there is only one minimal spanning tree on this graph, but it was only example. Yeah, you can repeat this proof, this explanation in the common case, of course.
But
Okay. Yeah.
this theorem is available even when the graph is directed.
If the graph directed, it is interesting question. Firstly, we need to understand what is the minimal spanning tree of the directed graph. And of course, we can find different different definitions of it, because as you know, we when we talk about depth first search, we talk that we have strongly connected components, and we say that there is, of course, there exists weak connected components. Remember it? Yeah. Difference between strong connected components and weak connected components.
Yeah.
So, of course, when we find tree as example, for example, we can find only that trees that has a root or a root vertex R, and each edge has a direction from in the direction in the root. Yeah, as you see that if we can, for example, sort this vertex by topological sort, each edge will have a direction from the right to the left, for example. Yeah, and for example, we can find only this trees and find in them minimum of the weight. Or we can, for example, say that, okay, we can forget that each edge has a direction and find minimal spanning tree in the graph that we can get if we forget the direction of the graph of the edges. Okay, or for example, if we had some edges, yeah, like this, we can have some strong connected component bigger than one vertex, for example. And for example, we can find and we say that each edge has weight. Yeah. And of course, if we forget about direction of the edges, we can say, for example, that we need to add this edge, this, for example, this edge and this. Yeah, and we have a spanning tree. Yeah, but now we in this tree we have now a vertex as a root that will be endpoint of each directed path, for example, yeah, because we have these 2 points that it is ancestor of this vertex, but edge connected these 2 points in other direction, not from the predecessor to ancestor. Yeah. Do you find difference between this tree and tree when we, for example, change this edge to the this edge? Yeah. Because if we change this edge to the edge that connected V and U, then we get a tree in which each edge starts in one vertex and go to the ancestor of this vertex in this tree. But if we look at the red tree, we see that in red tree, this vertex is an ancestor of V. Yeah? But edge starts in W and ends in V, not in the other direction. So, of course, in the directed graph, we have different definitions of trees that we can name as spanning trees. And when we choose one of these definition, then we get different algorithms about finding edges. And of course, if we find a minimal spanning tree as a tree in which each edge starts in process from vertex to ancestor of this vertex, yeah, then we say, for example, that it wouldn't be the tree with the minimal cost, because we can change this edge to this edge, yeah. But if we change it, we get a tree not interested for us class of trees. So it depends on subgraphs that we name as spanning trees of directory.
In this first graph, we will just assume that graphs are unedited.
Yeah, of course, да. Yeah, we say today that we work only with undirected graphs.
Okay.
Of course, if we in the directed case, if we forget direction of each edges, we get this case too. So about cut property, we talk about cuts today a lot. So we need to understand what it is. Do you remember when we talk about Ford-Fulkerson algorithm and find minimal cuts in the network? Remember it? When we say that, yeah, max flow and minimal cut, it is equal in the network when we work with it. Remember it? Or I need to open slides of the previous lecture. Hmm? Okay, now talk about it. Okay, and we said that cat is the partition of the set of vertices in two sets. Yeah, set A and set B, and edges that connect one set with other will be in the cat. Yeah. And then today we need to work with minimal spanning trees, and we can say and we can prove this theorem that we have some cut, one cut, and we have different edges that connect these two parts of the set of the vertices. Then if we find the minimum edge, we say that it will be in some minimal spanning trees in this graph. It is very important for today's algorithm that this theorem is true. And do I need to set an example to understand why it is true in the common case? Yeah? Okay. So, another graph. For example, we have these vertices as a part A and these vertices as a part B of the graph. And we have weights of for example. Yeah. Okay. Then I say that, for example, we have minimal spanning tree that doesn't contain this edge. Yeah, I can emphasize some spanning tree and say that it is minimal spanning tree. Okay. For example, if we can imagine that it is minimal spanning tree. Yeah. Then we can say that if we we can name this tree as ST. Remember, as in the previous slides. Yeah, T. is 3 is t. Okay, then we can add h with the minimum weight in this cut. What we get? What do we get in this graph? That is a union of 3t and he that emphasizes with blue color. What we get? Yeah. We get a cycle. Yeah. And of course, if we have he in the cycle, we have another edge of the cut in this cycle too. I can emphasize it with other color. Yes. Yeah. And we say that this edge has a weight bigger than this edge. And if we swap these two edges, we get a tree with the less weight than the tree T. Yeah? If we say that G with two primes, it is equal to T without this edge, for example, E with the prime. Yeah. Then we say that difference between these two weights equals to difference between E with the prime and E. It is bigger than 0, then weight of G of T, yeah. Yeah. Weight of T is bigger than weight of G with two primes. So it isn't minimal spinning tree. Yeah, yeah. So we can say that if we have
Both of them, they don't contain E.
Contain E? Which tree is not contained tree? This is 2 tree.
Yes, but you say that the weight of E minus
Yeah.
weight of T prime is equal to weight of T prime
Yeah.
minus weight of T.
And T contains E with the prime.
Yes.
And other edges. And G with two primes contains other edges and E. Yeah. Then we find difference of them. We say that all weights of other edges disappear, and there is difference between weight of these two edges. Understandable? Why we get difference between edges? As in the first example, yeah? And then we say that because of minimum of weight of this edge, it is bigger than 0. So we say that T isn't a minimal spinning tree. So if we have minimal spinning tree, it of course contain minimum edge, or if we have different minimum edges, we can say that it must contain one of them. Understandable? Yep.
In terms of weight of t minus weight of t double prime equal to weight of e prime. Like
Yeah. Why we set g prime as a t minus e prime?
For this row weight to that like weight of t minus weight of g.
Or you don't understand why as a consequence we have this equation, yeah?
I don't understand why it is equal to weight e prime minus weight.
Or why it is equal to it, yeah? Yeah. So we can say that we set the sum of the weights of these edges, these edges, is equal to S. Okay? Then we can say that weight of T is equal to S plus weight of E prime. Do you understand why it is true? Because T contains all these edges and this edge. Yeah? For example, to get a contradiction, we can say that it is a minimal spanning tree that doesn't contain edge E. And then we say that, okay, we have a contradiction. Or we can say that if we have some trees that don't contain this edge, it isn't minimal spanning tree. So minimal spanning tree contains, of course, E. Do I need to let this weight? Yeah. It is equal to S plus weight of E. And when we find difference, S disappears. Yeah. Understandable? Okay. Do you have question?
No.
Oh, nice. It's about cut property, and we use this property in most of the cases. For example, firstly about last property of minimal tree, about uniqueness, and if we have graph, of course, connected graph. Yeah, today we'll talk about connected graphs, because in yeah, connected and indirect and weighted graph. Yeah, and if all the weights are different, then we say that minimal spanning tree is unique. It is only one in the graph. Why? Why we can say that there is only one minimal spanning tree? Of course, it is simple to imagine, but it can be not simple to prove it. Can you prove it without text on the slide, for example? Hmm? Without text. No. On this slide we have proof, but I can swipe and ask you, can you prove the theorem that a minimal spanning tree is unique if all the weights are different. If you say that it is simple.
Yeah.
Or can you prove without text inside? It is simple, but of course it is. If we imagine it is simple, and of course today we will talk about different algorithms, and we see that if we have different weights in each step, we have deterministic step to the other, and so algorithm get only one minimal spanning tree. But all the algorithms that we get today will work with, of course, connected graphs with weights that can be equal. And for example, if we have no weights, we can find minimal, we can find any spanning tree if we set that weight of each edge equal to 1. Yeah. Then a minimum spanning tree, all spanning trees is a minimum spanning trees. Yeah.
When all the weights are equal.
Equal to 1, for example. If we have no weights, for example, and we ask ourselves that we want to find some spanning trees, we can set all the weights equal to 1 or equal to other constants, and then start algorithm that we the algorithms that we talk today. Okay. And can you prove?
I'm thinking.
Okay, and let's talk by induction. Yeah. For example, here we get. Yeah, I said another example. And set different weights. Okay. And by induction, I can say, firstly, I can say that this vertex will be in the minimum spanning tree. Yeah. And this vertex will connect with other vertices, for example, by some edges. So if I set this as the cut of the vertices of the graph, as you can see in the slides, on the slide, I can say that there is only one edge with a minimum weight, and by the previous theorem, yeah, edge with the smallest weight must be in minimum spanning tree. So I say, okay, I need to include this edge in the minimum spanning tree. Then I remove this. I have other cut.
Have a next minimum.
Yeah, and we find other, yeah, this. And it, because all of the minimal spanning tree must be contain this edge because it is minimum of the cuts or of the edges in the cut. Then I repeat this these statements. Yeah, I said that it is the other cut and say that this edge must be in the tree and repeat it. Yeah, I add this edge, this edge, this edge, this, and this. Yeah, and 18. Yeah. By induction, I can prove that all of these edges must be in the minimum spanning tree. And due to red color emphasizes a spanning tree, and all of these edges must be in all spanning trees, or minimum spanning trees. So I say that it is the only one minimal spanning tree in the graph. Yeah. Understandable. Okay. It's about uniqueness. Of course, if we have edges with the same weights, then we cannot say that there is a unique minimal spanning tree in the graph. And this is the example. Yeah, we have two edges with the same weights, and we find different minimal spanning trees. And of course, if we have in the graph weights with equal weights, of course, it isn't true that we have different minimal spanning tree. We can have in the graph edges with the equal weights, and in this case have only one minimal spanning tree. Do I need to emphasize this? Well, if we have a case when we have some edges with the same weights and we have only one minimal spanning tree. Yeah. You need. I can ask it in this theoretical test, and you need to understand how to find this example if I ask you.
Tree that has two weights.
Yeah, of course. Or we can say that all the weights of the tree is equal, and it is it will be the example when we have different edges with the same weights, but there is only one. Yeah. All trees with edges which have similar have only one minimal spanning tree equal to the tree. Yeah. If we have tree, we have only one spanning tree, and it will be minimum spanning tree. It doesn't depend on weights of the edges. So it's about uniqueness, and then we talk about first algorithm. Yeah, we have time to talk about. Of course, there are different applications of minimal spanning tree. And today we will talk about three classical algorithms, about Boruvka's algorithms, Prim's, and Krukals. Firstly, about Boruvka's algorithm. If we have, for example, vertex and different components that contain in minimal spanning tree, we can say that we find a cut when one part contains only one vertex and other part contain other vertices. Yeah. So if we employ this edge that connects with this vertex and has a minimum weight, it must be in some minimal spanning trees. So the algorithm equal to has three steps. Firstly, we say that firstly we say that each vertex will be in one component, will be in its own component. Yeah. So firstly, if we have n vertices, then we have n components. Yeah. Then, in the second step, we say that for every component, we can set this cut and find minimum edge that connect this component with other component, and find for every component such edge. Yeah. Then we say that these edges must be in the minimal spanning tree, and we add it to it, and then numbers of components will be less than on the previous step. And we repeat second step while we have more than one component. And when we get one big component, we say that it is minimal spanning tree. Understandable? So on each step we have spanning forest, and we in each step we connect two different components by the edge with the minimum weight. Yeah.
Is this similar to Krukal algorithm?
Not similar, because we can connect not similar. We'll talk about Krukal's algorithm, and it is similar to Krukal, but Krukal work with one big component and add to it different vertices. But in this, Krukal work with edges. Yeah. Krukal works with edges, and we find edges, and Krukal works with minimum edges with the minimum weights, and of course it get forests too in each step, and each step connects different, but Krukal find minimum weights and minimal edges with the minimum weights and add it to the first if it connects different components, and repeat it for every edge. We talk about it later. Don't get in the mind this explanation. We will talk about Krukal algorithms later. But in this case, we don't work with set of the edges and go through it from the minimum edge to the maximal. But we work with components and with the edges that connect different components. And we fight for every component edges with the minimum weight on it. So, firstly, we can say that we have a lot of components. Yeah, I didn't count number of these vertices, but we say that it is equal to 20. I don't know, 20, for example. Near 26, for example. I don't know. 20. Okay. I believe you. It is 26. It is 26 vertices on the slide. Okay. Then we say we have 26 components initially. Yeah. And we say, for example, this component connects with other components by 2 edges, 1 and 2. And then we say that we add this edge because it is minimum for this component. Then we repeat it for this and add this 2. We repeat for this, add this 2, for this, add this 2, and repeat for all of the edges. And of course, for example, for these vertices, edge will be equal to different components. We connect this component with this by 1 edge. Yeah, but for example, for this vertex, we can add, for example, this edge or this edge. But for this vertex, if we add this edge, we can say, okay, there is edge that has minimum weight, and we add it too. Yeah, so we can add edges that connect this vertex with this component and this component too, because this edge will be minimum for this vertex and this will be minimum for this vertex. So, for example, yeah, for example, we can see that after one step we get this big component because for this vertex it is a minimum weight edge. For this vertex it is the minimum weight edge, and for this it is 2, and for this it is the minimum weight edge. And of course, when we add, we need to union components and firstly try to find if these components are equal, of course. Yeah. So we cannot get a cycle in the components. So we repeat it for new components. Yeah, we say that these new components, and we have a cut this, and we add, for example, this edge or this edge. We have this cut, and we add this edge because it is a minimum cost in this cut. Yeah, and repeat it for all new components. Yeah. After first step, we have 1, 2, 3, 4, 5, 6, 7, 8. 8 components. Yeah, and then we add this edge, this edge, this, and this. Yeah, because this is the minimum in this cut, this minimum in this cut, this minimum in this cut. Yeah, in this cut. This minimum for this cut, this minimum for this cut, this minimum for this component, for this component. Yeah. So we get 2 components now. And then we have only one cut with graph, and we find the minimum and add it and have a minimal spanning tree. Okay. Yeah, it is Boruvka's algorithm, and it's about about complexity. Firstly, yeah, we can say that in each step we repeat finding the minimum, the edge with the minimum cost for every edge. Yeah. So and number of steps has asymptotically number equal to O from logarithm from number of vertices. Why? Because in each step we connect one component with other, and number of components in each step will be decrease into times or bigger than 2 times. Yeah, we can say that firstly we have 26 near 26, yeah, 26 components. Then we have 8 components. Then we have 2 components. Then we have 1 component. Yeah, and we can say that the if we divide 26 by 8 or 8 by 2, 2 by 1, all these numbers must be bigger than 2. And so it decreases as exponential function. Yeah. So we get only 4 steps here. This number equal to log by 2 of 26. Yeah, it is equal to 5, between 5 and 4, or with, yeah. So it is near number of steps, and bless you, and logarithm from number of vertices. So in each step we spend O from number of edges time. So we can say that total time is equal to O from number of edges multiplied by logarithm from number of vertices. Okay, and we have time to talk about disjoint set. Or we get now break time, or in, for example, 15 minutes. Do we need now a break? Or we'll talk about disjoint set and then take a break? Okay, I can continue. And about important data structure that we can use in this algorithm and other algorithms that connects with um, cut property. That if we have some set, for example, set of vertices, we can divide it into disjoint set of subsets. Yeah. For example, we can say that if we have set of numbers, yeah, or we can divide it, for example, into these subsets. Yeah. And we need to get to implement data structures that will store these subsets and can union of them or compare them is, for example, 2 and 4 in one subset or not. Yeah. For example, we can ask data structure if some numbers or vertices in one component or in the other. Yeah. So name of this data structure disjoint set, and idea is equal to store different subsets and use, for example, trees, binary trees or Fibonacci trees or heaps to store each component. Yeah, you can use different graph in it, or different or you can use lists, for example, to store subsets. We talk about it now. And about implementation and about functions that we need to implement. Yeah, we need to implement firstly making set. Yeah, as in the Boruvka's algorithm. Firstly, we make set of all the vertices. Yeah, by we say that each vertex has its own component. Yeah, so we need to have a function make set. Then we need to get parents of the set, for example. Yeah, for example, in this case, we can store, for example, this subset as a tree. Yeah. And we say that it is a parent for all the vertices in this subset. Yeah. And it is important that if we get find function from different vertices and we compare it, if this vertices in one component, parent is equal, and if vertices in different subsets, parents will be different. Okay. So for example, we can implement find as this function for example, if for each vertex we know what is the parent of this vertex. Yeah, if we have a tree, we can say that 2 is the parent of 4, yeah, and we repeat it recursively while we didn't get that we didn't get a root of the tree. Yeah, it's about find. It is important, of course, function because we need to use it in union. And as you remember, we union different components. Yeah, we have subsets, and then say, okay, we add this edge, and we need to union these subsets. Yeah. So to union, we say that, for example, if we want to union subset S with index 2 and subset S with index 3, yeah, for example, this is 2 a binary tree. So we firstly find parents or roots of these two trees. We compare size of these trees. Yeah, we can store it in this class 2. In each node, we can store size of the tree as depth of this tree. And then we compare and say that, okay, depth of this tree is equal to or 1. If you count levels, it will be equal to 2. If you count edges, or the most the longest path from the roots to the other vertices, it will be equal to 1. Yeah, and to compare, and you say that root has new new node that will be linked with it equal to 3, equal to root of the set of with index 3. Yeah, so by the union we say that parent of 3 will be equal to 2. And then we have new
We could also take
2 to link to 3.
yeah.
Yeah, if it is equal, it will be it depends, for example, it is minor or equal, yeah, for example, and it isn't important in the union, but then we have a new tree that contain all the vertices, yeah, and it will be new subset equal to union of these subsets. So it is implementation of function union. Yeah. It is equal to example that I told now. Any questions about this implementation? As you see, we need to store parents for each node and size as the size of this tree at the depth of this tree. Yeah. Or for example, we can, if you see, we store size only for roots, and we need to change only for roots the size. So, for example, if we ask what is the size of the tree, yeah. For example, if we get 5 products and we ask what is the size of this tree, what will you do?
The number of elements or
Oh no, it is the depth of this tree. It's 2. Why? We store in this element size equal to 0 because we don't know, we don't have any vertices that connect with this vertex. But we can say that size of the tree equal to size of the root of this tree. So if you use size of the tree that you use to store one component in your algorithm, you can ask what is the size of the node that is the parent of. So for example, yeah, of course. So for example, to ask what is the size of tree contains vertex v, it will be equal to find of v point size. Not v point size. Point from size from parents or root of this tree. Understandable? Okay. And it's about implementation. And next algorithm we'll talk after break. And firstly about question of contest to record it too. Yeah. It's about exercise from the one of the previous contests. Exercise names as perfect square, and when in this exercise you need to find a presentation of the number as the sum of different squares, or not different, or sum of minimal numbers of squares. Yeah. For example, for 12, it is equal to sum of 3, 4. 4 plus 4 plus 4 equal to 12, and you can find a difference, or you can find two squares of integers that in the sum get 12, or one square that gets 12. So how to use breadth first search in this case? You can set the graph that contains vertices equal to numbers from 0 to n, that is given in the input of your exercise. And then you can connect vertices with edges. For example, 0 and 9 we connect because the difference of them equal to 9. That is the square of integer. Yeah. So then we get a graph. Of course, you can set the direction of these edges, and you get you get directed a cyclic graph, for example, and you use BFS in this case. And for example, for 12, you find that the shortest path from 0 to 12 equal to 3, and it goes through the vertices 4 and 8. Yeah. So we can say that 12 represents as the sum of the difference of numbers in the vertices, in the sequence vertices. So we say that difference between 4 and 0 equal to 4, between 8 and 4 equal to 4, 2, and between 12 and 8 equal to 4, 2. Yeah. So 12 represents as 3 squares 4, 4, and 4, and you can find in this graph path from 0 to 12 length of which equal to 1 or 2 or 0. Yeah, and so it is the minimum representation of 12. Yeah, understandable. Okay, return to our lecture. Next algorithm names as Prim's algorithm, and idea is similar to Boruvka's algorithms, and we can say that if we have already had some subgraph that is a tree, not spanning tree, but tree, we can set a cut that divided our graph into in one part we get our tree, in other graph we have a residue of our graph. Yeah. Then we say we have minimal edge in this cut, and we can add it to this tree with this vertex and repeat this algorithm. And as a result, we get minimal spanning tree. So it is a greedy algorithm. When in each step we find the minimal edge in the cut that we can add to this tree. So about sorry, oh, nice. So about algorithms. Firstly, we say that one vertex it is 2, 3, yeah, and we start with it. As you remember, when I proved that we have only one minimal spanning tree if all the edges have a unique weight, yeah, I say that we have this cut, etc. I add in each step edge in that is the minimum in this cut. So, sorry. So it is Prim's algorithm as the example. Yeah. So we in the second step of the Prim's algorithm, we grow our tree, and we add edge that has a minimum cost in the cut, in this cut. Yeah. And we repeat second step before we get a minimal spanning tree. So, about example, I draw step by step all the algorithm. It was hard, but I can represent. You see, firstly we have only one vertex. It is arbitrary vertex of the graph. You can choose other vertices initially, but I choose this, and I say we have 2 edges in the cut, and what is the minimum of 1? Yeah. So we add this edge, and we get this new tree and this new cut. What is the minimum edge in this cut? 2. In this cut? In this cut? Oh, and we have 1, 2, 3. And you remember that if we have different edges with minimum weight, for each edge we can find minimal spanning tree that contains it. So you can choose any of these edges. I can choose this edge because we built minimal spanning tree in the previous series, and I want to represent that different algorithms can find equal minimal spanning trees. But of course, if you choose this, you can repeat steps or second steps, and then get another minimal spanning tree too. So I choose this one. Yeah, and we can add this or this. Yeah. And of course, I need to color this. I forget it. Then add this. Then we have this point, yeah, equal to and repeat it, yeah. And we get a minus by 2.
So if we get both case, we might get different.
Yeah, of course. And if you see, for example, in this minimal spanning tree, you can choose not this edge or this edge. You can swap these two edges, and you get other minimal spanning tree. And of course, if in this step you choose this, you get other minimal spanning tree. And so it's minimal spanning tree that you get from previous algorithm depends on source vertex and depends on each step. If you have edges that have equal weights, yeah, it's minimum, yeah, because it is gritty algorithm, and in each step we get the minimal of the cut, and we proved before that there is cut property. Remember, in each algorithm it is the main part that theoretically prove why we get a minimal spanning tree. Yeah, in Boruvka's algorithm we get we add edges between different components. In this case, we add edges that includes in cut in one part of each we have a tree, and in the other part other subgraph. And you can see, for example, now part B in this cut isn't connected. So of course it isn't important to get connected components in each part of the cut. Yeah, you can, but in the Prim's algorithm, in one cut we get in each cut in one part of the cut we get a tree, so it is connected, but other graph can be unconnected. And we repeat it. Yeah, it's about pseudocode. It is it's of course simple because I add all the difficulties of this algorithm in this row, yeah, in this line, because if our tree isn't a spanning tree, we say that we find our edge with the minimum cost, with the minimum weight on it. And of course, to find this, we need to understand what is the edges between two components. Yeah, we need to go through it and find edge with the minimum cost. And so in the implementation, it isn't one row, of course. You need to, for example, to implement some function that get graph G and, for example, subgraph U. Yeah, and then return the minimal or the edge with the minimum weight in the cut. Okay. So you need T and U. Okay. Interesting question. As you see in this line, that T we grow with edges, and U we grow with V. So of course it is T is equal to a set of edges in this minimal spanning tree, and U is equal to set of vertices. So we repeat our algorithm while vertices is equal to vertices of the initial graph, that it is equal to that our tree is a spanning tree. So about complexity of Prim's algorithm, as you remember, some algorithms depend on implementation and that data structures that you use in the implementation. And Prim's algorithm Prim's algorithm has a different asymptotical time if you use different data structures. So you see that in the worst case, asymptotical time is equal to O from number of vertices in the square. Do you understand why it is? Why it is equal to O from number of vertices in the square? Yeah, for adjacency matrix. Why time complexity is equal to?
You explained it in the first lecture.
Okay. Yeah, okay, yeah. And of course, to store matrix, we need to spend O from number of vertices in square. But why in the algorithm we spend this time if you use adjacency matrix?
Like we need to look on the edge. Like we need to look on the edge.
We use adjacency method to find the smallest way. The O of V square is used to find the smallest way.
The smallest weight. Okay, we can say that, for example, we repeat our steps all from number of vertices times. Yeah. For example, this graph contains 26 vertices. Yeah, and so we repeat 26 times second step of algorithm. Yeah, this. So when we have a cut, how to find a minimum weight? I can say that we can spend only O from number of vertices time. Why? Because initially for every vertices we can find the edge with the minimal cost, with minimum weight. For example, for this vertex it is equal to 1, for this vertex it is equal to 1, 2, for this 1, 2, for this 1, 2, for example, for this 2, this, yeah, etc. And then yeah, and then when we add different vertices, for example, this, we can say for this vertex the minimum equal to 2, for this equal to 3, and so we can find minimum of edges from the minimum for each vertices in this tree. But of course you can see that for example in this cut this edge not is the minimum for this vertex, yeah, for this vertex edge that connect to this vertex with minimum weight is equal to 1, but in this cut we add this edge, so we need to swap this weights.
We needed to start, I think, if you take note,
So you can
storing all the regions, sorting them, and each time we take
so
one,
we need
just
to spend O from number of edges log edges time, yeah, for example. So it isn't equal to O from number of vertices in square. It is bigger than O from number of vertices in square in the worst case. But you can you can think why we can get this asymptotical time if we have adjacency matrix. So let's go through it. Yeah. You can remember that if you use different data structures, you get different time complexities. It is the main idea of this slide and of most of the most algorithms that we talk about. Yeah. And so we talk about Fibonacci heap on the next lecture, I think. So about the last algorithm for today, it's about Kruskal's algorithm. And idea of it is that we can we have Boruvka's algorithm, we have Prim's algorithms, and we can make new algorithm as the union of them. Yeah. For example, we can find the minimal edges in the graph, and we can add it to the minimal spanning tree because each minimal edge in the graph needs to be in the minimal spanning tree. And we add edges with the minimum cost, with the minimum weight. Then we repeat it while we don't get big component that is equal to minimal spanning tree. So the main idea is that if in the graph you can see there are different edges with the weights, but this edge has the minimal weight on it. And so in each minimal spanning tree, this edge will contained, will be contained. Yeah. In the Krukal algorithm, we make the disjoint set, yeah, as in the Boruvka's algorithm of the vertices in the graph, and then we connect them not as for each component we find the minimum cost. Yeah, for all vertices we find edge with the minimum cost, with the minimum weight, and we add it to the our tree, and then we connect different components and union them and repeat it while we until we get a tree. So, firstly, about our example, yeah, about our graph that we talked about in the previous algorithms. We see that initially we have 26 components as in the Boruvka's algorithm, but now we connect components that are connected with the edges with the minimum cost. Yeah, you can see that is this, and these edges have the minimum weights on it, and we add it. Then we repeat. Yeah, we have now less than 26 components, and we add edges with the weights of 2. But now we need, as you can see after this step, of course, about, for example, 3 edges with weight equal to 3. We say that, for example, for these 2 components, we have these 2 edges with weights equal to 3. And we can choose one of them, not both of them. If we choose both of them, we get a cycle, and we don't want to get a cycle because we want to find a minimal spanning tree. So if we have between 2 components some edges with the minimum weights, we say that we choose one of them. Understandable, yeah? We add with the 3, we repeat it for 4, then for 5, for 6, and you can see that after it we get the same minimal spanning tree. Yeah. So it's about Krukal's algorithm. Yeah. Do I need to make an example about Krukal's algorithm, or this is understandable example? Or we can wait for your colleague and then ask her to. And then we talk about pseudocode. You can see it, and you can see that it's very similar to Boruvka's pseudocode. Remember it? Do we have? Oh, we don't have pseudocode. Yeah. But to imagine how to implement this algorithm. Firstly, we make set of these vertices. Then, for each set in the disjoint set, we find the minimum weights of the edge with the minimal cost, and we add it and repeat for each component and repeat while we don't have one component. So it's about Kruskal's algorithm. Do you understand how it works? Firstly, we make a disjoint set of all the vertices, as in the first algorithm, in the Boruvka's algorithm. And then we add edges with the minimum cost, and we get new components. And then we repeat for next weights, for weights 2. And for example, for weights 3, you can see that there are two edges that connect two components with the weights 3 is equal to 3. And we choose one of them. If we have 2 or 3 or more edges that can connect in one step different components, we choose one of them randomly, for example. And then we get our minimal spanning tree in some steps. I union different steps in this picture. Of course, on the next step you add these edges with the weight equal to 4. Then for 5, for 6, and then with 12. And we get this minimal spanning tree too. And as the implementation of it, firstly we say that our tree is empty, we have no edges in it, and we make disjoint set of all the vertices. Then we order all the edges by weights, and for each edge, for example, firstly, we ask ourselves, or we ask in the program, this, for example, vertex U, this vertex V, and so we say that they are in the different components, so we add this edge in one. We add this edge in the our tree, and we union these two sets. You can see. If they're in different components, we add this edge in the tree, and we union these two components. So then we see that this edge connect different components, we add it to and for others. Or for example, in this step, firstly, we add this edge, for example, and then we ask ourselves, is this edge connects different components? No, because after we add this edge, we have one big component, and for this edge, you can see that this O and V in our forest, in this step, connected, have already been connected. So we don't add this edge in the forest, because this vertex and this vertex have been already in the one component. So we repeat for each edge of these 3 lines, and in the end we get one big set equal to set of vertices, and in the F we get our minimal spanning tree. We store our minimal spanning tree that we get as the result of this algorithm in structure F. So you can see that our cycle repeats O from number of times, and if you remember, find set has asymptotical time equal to O from log of number of vertices, because it is equal to 3 in it. So Kruskal's algorithm spends O from number of edges multiplied by logarithm from number of vertices time. So it is equal to Prim's algorithm. Yeah. Yeah. But I think in the worst cases they are equal. And I think this time should be multiplied by logarithm from number of vertices too, because of sorting of the edges. So it is all about today's algorithm, and I think we will talk next time about Cartesian tree, Fibonacci heaps, or different other data structures that we can that you can use in these algorithms. And in 2 weeks we get our first theoretical tests.